Okay, so now let's move from kinematics to quantum dynamics. In while starting quantum mechanics, you start usually the conventional approach is to start with kinematics, and in kinematics you talk about postulates of quantum mechanics. And when you talk about postulates of quantum mechanics, then they involve two very important concepts regarding those postulates. That is, they involve Hilbert space of states, and the other thing is basically observables in quantum mechanics. And so one needs to keep in mind that when you discuss quantum kinematics, the usual or the conventional starting point is to write postulates, quantum postulates. And what those quantum postulates are actually about, they are about the Hilbert space of states, and obviously which describe basically the states of the quantum system. And the other thing which is very important are the observables. When we talk about observables, then they are basically some Hermitian quantities, some real quantities, some measurable quantities, and associated with those observables are operators. So these two are very important quantities. And so if you make a transition from quantum kinematics to quantum dynamics, then you need to have a discussion which basically involves how the states evolve in time. And when you talk about how the states evolve in time, then you need to discuss the operators as well. So you see, when we talk about quantum mechanics, what I'm trying to sort of emphasize here is to say that there is a same description with a change, that now that description include evolution of the quantum system in time. So quantum dynamics is basically the discussion or the procedure where we would like to see how the states evolve in time. Yeah. And so one would like to define quantum dynamics. So quantum dynamics describes uh, describes how quantum or the states how the states evolve in time, evolve in time. So that is some procedure where we talk about the evolution of quantum states in time. Yeah. And then we need to talk about, so similar to quantum kinematics, we need to talk about some postulate, and here we need to talk about a postulate which is the time evolution of postulate. So this is basically described by uh, that is how the states evolve in time is basically nothing but a postulate of quantum mechanics. Yeah. And so this is nothing but some differential equation. This is uh, some differential differential equation, or the time evolution equation, involving uh, ket vectors uh, with time derivative. Yeah. And this is nothing but, i.e., time dependent Schrodinger equation. Yeah, so this is time dependent Schrodinger equation. And how do you write it? So this is our famous equation iota h bar d by dt, some ket vector psi, which is equals to the Hamiltonian times the ket vector. And where this Hamiltonian, which is an observable, जैसे मैंने आपसे शुरू में कहा, whenever we start with quantum mechanics we start with postulates, and two very important concepts are the space of states, that is the Hilbert space, and the observables, and these observables are associated with operators, and so the operator here we are talking about is the Hamiltonian operator. But now we would think about this Hamiltonian operator as some operator which is a function of time. So here in this expression, H is the Hamiltonian, which is an observable, and which gives basically gives energy of the system. Yeah. And obviously, when we talk about energy of the system, and then this particularly would correspond to some operator, and this operator would be some Hermitian operator. And in particular, because we are talking about some a real quantity, is a Hermitian operator. Hermitian operator. Yeah. Now, uh, here in this particular case, that is when we are talking about time evolution, then in general, this h would be a function of time. And so, uh, since we are talking about time evolution, so this h would be, h is in fact h of t, and this h of t means IE may be time dependent. Yeah, so we are talking about maybe, we would come up with this why we are using maybe, because since we are talking about time evolution, so why using the word maybe? So there are different approaches in quantum mechanics, वो हम बात करेंगे आगे चल के. Okay, so although there are systems which have time translational symmetry, and hence the Hamiltonian and the energy will not depend upon explicitly on time. So in those cases, we would think about that. In fact, rather than talking about Hamiltonian as a function of time, because there we have some sort of a symmetry, let's say time translation symmetry, and so in those cases the energy would be conserved. But then we are explicitly talking about cases where h is a function of time. So one of the cases, the harmonic oscillator, where h is a function of time. So regarding this maybe, we could give two in fact comments. So although there are systems where which have time translational symmetry. Translational symmetry. What does time translation symmetry means? That is, uh, when we talk about translation of time, the system remains unchanged. Yeah, and in those cases, the Hamiltonian energy will not explicitly depend upon time, and so the energy would conserve. So for such systems, the Hamiltonian and energy will not have will not have explicit time dependence, have explicit time dependence. So the energy is conserved. Energy is conserved. Yeah, so uh, those are those some cases जहाँ पर हम ये बात कर सकते हैं. But there are certain other cases. What are those other cases? But uh, what are those other cases? We have systems where such as harmonic oscillators, oscillator, which have explicit time dependence. Explicit time dependence. Yeah. And so in those cases, the Hamiltonian is time dependent. So we could say, so in such cases, Hamiltonian is time dependent. Uh, Acha, we could think about such systems. For example, we could think about the early universe, where the size of the universe is a function of time. In some where the size of the universe is changing and it is a function of time in some very rapid manner. So, if one wishes to describe the quantum system, quantum mechanics of particles in early universe, then one would effectively talk about the time dependent type of the Hamiltonian rather than time independent. And so, in such cases, those cases are basically relevant to harmonic oscillator. So, time dependent Hamiltonian operators, they appear in some physical problems, not just in the case of early universe, but time dependent Hamiltonian also appears in some physical problems one where one need to solve the Schrödinger equation as a function of time. Yeah. So so we have a number of numerous cases, or one of the case हम यहाँ पर भी करेंगे, not one of the case but interesting cases हम इस टॉपिक के अंदर डिस्कस कर रहे होंगे, जिनका ताल्लुक जो है वो इनफैक्ट इलेक्ट्रोमैग्नेटिक ऑसिलेशन से भी है. इलेक्ट्रोमैग्नेटिक ऑसिलेशंस आर टाइम वेरिंग ऑसिलेशंस. And so we would talk about as applications of these topics आखिर में, जैसे for example transition probabilities, Einstein coefficients, absorptions and emission processes, spontaneous emission, stimulated emission, laser, and all these are basically examples where we need to solve the time dependent Schrödinger equation. So uh, one could also think about as an example, uh, time evolution of early universe, which is a system of particles where the size of the universe is very rapidly changing, and this rapid change in fact is a function of time. There could be other physical problems. For example, electromagnetic oscillations, जहाँ पर हम where where time dependent Schrödinger equation is solved. Is So, so uh, this is one way of discussing, uh, in fact, those systems which have some time dependency. And discussing those systems means how that those systems are evolving, discussing how those systems are evolving in time. Then there could be some alternate way as well, and that alternate way of describing such a system, or in fact this postulate, which is particularly associated with the time evolution of the system. And those alternate ways not is, is is not are not the ways where you write Schrödinger equation, but you simply say that if the state of the system is described by some state vector psi of t, then this psi of t is, or this state is not just a function of the space coordinate, but it is also a function of time coordinate. So the ket vector would then have the time dependency as well. Then that ket vector is a state at time, would describe some state of that quantum system at some time t, and then that state of the system at time t is related to the state of the system at some later time. Let's say we call that time t prime, by the action of some operator. And in that case, when we are talking about the state of the system being related at time t to time t prime, then that can only be related by some operator which is a linear operator, linear in time. That is, the system is going from time t is equals to t to time t is equals to t prime, let's say. Yeah. So this is an alternate way where, rather than solving a Schrödinger equation, you write this state function in terms of some linear operator, which we call as a unitary operator. Uh, so alternately, we could think about alternately. Uh, Rather than describing the, sorry, the time evolution, the time evolution of a quantum system by a Schrödinger equation, one can simply say that if the state, sorry, if the state of the system is described by psi of t, then one can write this state as um, psi comma t as a ket vector is the state at time t. Then that state of the system at time t is related to the state of the system of the system at some later time t prime. Yeah, by the action of of some linear operator. Let's say we call it as u as a function of t comma t prime. T comma t prime का मतलब ये है कि the system goes from as time evolves, the system goes from at time t is equals to t to time t is equals to t prime. Yeah, and so one would write such an equation rather than writing Schrödinger equation, which also gives you the time evolution of a system. You could write time evolution of the state of the system. So the important thing about as in kinematics, that you specify the space of a state, which is the Hilbert space, and then you associated observables, and associating observables means you write operators. So the basic or the bottom line of in fact a dynamical description of a quantum system would be to say that what is the procedure that the system would evolve in time. And so you would think about that differential equation, which is the time dependent Schrödinger equation. But then there is an alternate way where you would say, okay, there, if we define some state of a quantum system, and that state is some ket vector psi comma t, then you would ask a question how that state vector evolves at present at time t and evolves into some other state at time t is equals to t prime. And so you would do this, or you would find this evolution, time evolution of this ket vector by multiplying that ket vector by some operator, which is some linear operator in time. And that linear operator is basically, we call it as a U or unitary operator. So one could write then a simple equation that is the time evolution equation, that is the ket vector, can be written as U of t comma t prime operating on psi of t prime. So this is uh, that is basically the system is whatever. So we would think about the system goes from time t to t prime, or from t prime to t, whichever is basically is taken initially. But that is the same thing. So since Schrödinger equation is a linear differential equation, but one this concept of linearity, जब हमने linear operator की बात की, and that the reason behind is basically the Schrödinger equation is a linear differential equation. The operator has to be also linear. Uh, the linearity of operator is due to the fact that the Schrödinger equation is a linear differential equation, is a linear differential equation. So that's how. So these are the two approaches. One of the approach, as you see, one of the approach for discussing time evolution is by virtue of the Schrödinger equation, time dependent Schrödinger equation, and the other approach is by way of writing or describing some linear operator. So if one wants to relate the state of the system at time t with the state of the system at some earlier time t prime, let's say initial time is t prime, then one operates the state vector by some linear operator known as u of t, and this operator is known as the time evolution operator. Yeah, and when we say u is time evolution operator, it must be a unitary operator. That is, unitary operator का मतलब है कि it the scalar product is conserved. Yeah, हमें ये बात भी साबित अब करनी है कि यूनिटरी ऑपरेटर जो यू ऑपरेटर होगा वो यूनिटरी कैसे है, और इसको साबित करेंगे, दैट इज यूनिटरी ऑपरेटर. सो वन वुड से that u is a time evolution operator, and it must be uh, must be a unitary operator. What is a unitary operator? That is, scalar product is conserved. Is conserved. This is basically the definition of, so यहाँ पर u जो लफ्ज आ रहा है उसको हम यूनिटरी से ले रहे हैं. सो आपके पास, आपको ना ये समझ लेना चाहिए, दैट इज वी हैव this concept where either we could describe the time evolution of a quantum system using the Schrödinger equation, or we could describe the time evolution of a quantum system using a linear operator, which is known as a unitary operator. Now, as how it is unitary, or why it is unitary? How do we say that it is unitary? So we have to prove that this operator is unitary. So let's say uh, unitarity, unitarity of unitary operator. लेट्स से ये साबित करते हैं ना, छोटा सा ये बीच में एक आर्टिकल आ गया, बहुत इंटरेस्टिंग आर्टिकल होगा, इससे आपको बहुत सारी चीज़ें क्लियर होंगी अबाउट क्वांटम मैकेनिक्स. जब हम करते हैं बहुत सारे कॉन्सेप्ट्स एट लोअर क्लासेस वो आपको क्लियर नहीं होते, लेकिन एज यू गो अलोंग विद योर अंडरस्टैंडिंग ऑफ क्वांटम मैकेनिक्स बहुत सारी चीज़ें क्लियर होना शुरू होती हैं, एंड देन आपको फिर क्वांटम मैकेनिक्स में मज़ा आना शुरू होता है. अदरवाइज इट 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 रिमेन्स एज एन एब्स्ट्रैक्ट सब्जेक्ट अकॉर्डिंग टू सम पीपल, बट इट इज़ नॉट एन एब्स्ट्रैक्ट सब्जेक्ट, इट इज़ as real as classical mechanics. So let's say assume that the state at time t is normalized, and when we say the state at time t is normalized, then the scalar product of the state vector with itself should be equals to 1. So let's say uh, assuming that the state at time t is normalized. Normalized मतलब क्या है? That is, we take the inner product of this state with itself, that is bracket formation. This is equals to 1. And when we say it is equals to 1, then it is also known as unit normalized. Yeah. So this implies unit normalized. Yeah. So that, for example, if what does this unit normalize means, or the state is normalized, इसका क्या मतलब है? The इसका मकसद होता है, we talked about this normalization equals to 1. That is, the particle is somewhere. In case of kinematics, we talk about particle is somewhere. या सो दूसरे लफ्जों में द जो टोटल प्रोबेबिलिटी है वो कंजर्व है, द टोटल प्रोबेबिलिटी इज 1. So that, for example, if one wants to compute the probability of some observable A having an association with some operator capital A, let's say, as a function of time in the state psi, then that is just equal to the norm of the eigenstate. And what is the norm of the eigenstate? That is the absolute value squared. Yeah. And so when we say that this the state is unit normalized, then इसका मकसद ये होता है कि one needs to compute the probability of some observable. So we could write this mm, in wording, so that so that uh, for example, if the if one wants to wants to compute probability probability of some observable A. Yeah, uh, that is we find some observable A as a function of time t, let's say, in the state psi, in the state psi, that is just be equal to to the norm, to the norm of the eigenstate. What is the norm of the norm of the eigenstate? What is the norm of the eigenstate? The norm of the eigenstate is nothing but the absolute value of the scalar product of the state with observable A to state psi comma t whole square. And this is basically equals to हमने क्या किया? The probability that this state has an observable A. Yeah, so this is the in fact, you know, when we say that it is unit normalized, we say that the probability that the system is has an observable A, that is just equals to the norm of the eigenstate. And what is the norm of the eigenstate? This is known as this is basically the norm of the eigenstate. Norm of the eigenstate A. Yeah, yeah. And then the statement that the sum of all probabilities of some observable summed over all possible eigenvalues has to be equals to 1. And that is basically unit normalization. So, and then one would say, uh, yeah, then the statement, this is basic statement of quantum mechanics, that the that is the particle in kinematics we used to say that the particle is somewhere in some volume. Yeah, so that is then the state that the sum sum of possible all possibilities rather, sum of all possibilities of some observable summed over all possible path, summed over all possible eigenvalues, that is possible paths, possible eigenvalues has to be equal to 1, has to be equal to 1. Yeah, this is the basic in fact idea. So we are trying to relate the unit normalization concept with the total probability. And this is just the consequence of the fact that the state is just unit normalized. And so in fact, this is consequential, is, sorry, is just the consequence, consequence of the fact, the fact that the state is unit normalized. Unit normalized. Yeah, so this is something which is very important. And so, in some explicit or in some mathematical manner, computing, when you compute the sum over A of P of A comma T, that is total probability. And so, what is basically obtained is a summation of all probabilities, and summation of all probabilities would could also be written as in terms of some projection operator. So one could say in some explicit mathematical sense. Yeah. So in explicit, यानी देखें एक बड़ी इंटरेस्टिंग बात है. We talk about the inner product, we talk about an outer product. Inner product से हमारी मुराद होती है when we talk about some scalar quantity, and outer product से मुराद होती है that is we would like to project the system or may transit a system to some particular eigenstate. Yeah, or transfer the system to some particular eigenstate. And that is basically, in fact, the task of an operator, जिसको क्या